Great. Hello. Nice to see some people joining me for the live stream as always. So thank you for that. It's always appreciated. Getting down there to not very many meetings left, which is probably welcome news from your end. Okay, so we are in what, week 15. So we have this week and next week, and then your second project is due on December 11th. And then we have the final week of the semester where I will just do a normal week of content because I do want you to see how floating point numbers work on the x86 processor. I find it pretty interesting. So that'll be how we close out the semester, is by looking at floating point values on computer processors. So before I do anything else, and I apologize for this, one person has submitted a project, so I'm willing to be flexible about that. But um, someone brought it to my attention this morning that the setup of the project is not the best in terms of being able to test values. So you'll see there, project for minor updates. I consider them minor updates because in two places it's really just a matter of changing the range of things. And then also the sequence for computing the average is a little bit different because when I talked about it last week, I had it in my head that we were doing int 16 values, but it was also brought to my attention that we're doing int 8 values on the project, so that changes the computation. So I'm going to go through that before we do anything else, just show you how the project has been updated. So I did it in both classes. So both classes, you'll see an announcement here where I call your attention to the fact that I have made some adjustments to the project so that you can better test your algorithms. So let me go to the project. Why did I put project 4? I don't know. I put project 4. Can I edit it? I want to edit it. Yes, I can. Project 4, project 2, project 2. It's project 2 that I made the changes to. So project 2, there are small changes. And let me go ahead and fix the other class so that everything is all on the up and up. Two, and 2. Yeah, apparently I'm just getting all messed up here, coming to the end of this semester. Okay, so what are the changes to project 2? I have marked them. So they both have this tag that says updated on them, and they're also on the agenda right there. So turns out, thanks for that, for bringing this to my attention this morning. You can actually, rand.urange will generate random values in the negative range. So what we're going to change is we're going to generate our random values between -10 and 10. I'll do that in my example, just to, I can use it as part of my content today anyway. So you can actually generate down into the negative numbers using the HLA random library. So we'll generate random numbers between -10 and 10. So why those two values? We have signed 8-bit integers in our array, and the maximum possible value size of our array is 10 cells. So we have 10 possible at a maximum of signed 8-bit integers. And what I want to try to do is avoid situations where the values wrap around on themselves when we are computing the sum and the average, which would screw everything up. So to prevent the sum from being smaller than -128 or bigger than 127 in a possible array of size 10. So if you think about it, a size 10 array, if I generate random numbers and they're all 10s, 10 tens is 100. And that's good to kind of push up to the limit of possibly a positive 127, so that when we sum, if we were to get 10 random numbers that were all 10, then the sum would be 100 and the average would be 10 and everything would work out great. Same goes on the negative side. So if I have 10 negative 10s, the sum would be -100, which is well within the range of an int 8, so that if we were to sum them together and then average them, that all works. So that's why we pick those ranges, is because if a person were to pick the maximum size of the array and for some reason the random numbers generated themselves, all 10s or all -10s, we won't overflow the int 8 size when we do sums and averages. And then I decided to go ahead and just make that consistent with the user input as well. So we'll just limit the user to -10 to 10. And that way the user can't accidentally, during testing, enter values that would accidentally cause the sum to wrap around on itself, either from the positive end or the negative end. So anyway, that will make your testing life a lot easier because you will get actual sort of correct answers when you compute sums and averages. If we let those ranges be just a little bit bigger, there's always the potential that we would be too small or too big and our sums and averages would be all broken. Okay, so that's the big thing. That's in the announcement now. It says Project 2. And that's also on the agenda today, those ranges. And that will make it so you can more effectively test your algorithms. The other thing that was brought to my attention is that I had screen captures that were computing probably UNS 32s. So I didn't change my screen caps. I just am pointing out to you here that my example was written probably for UNS 32, although I can't remember because it was back in August when I did it and I didn't have time today to look at that. So anyway, just to note, the example is having to scale the size of the array for 4 bytes per element. In your project, you don't have to technically scale because every element is just 1 byte. So that's updates to the project. Hopefully that doesn't confuse anybody. But that does make your life easier. So I'll try to contact the one person who has submitted a project and just to let them know that if they want, they can go update it and submit an updated version, which I think you can just do. But anyway, for everybody else, since you haven't submitted, please take note of those changes. It will actually make your life easier on your end. And then for the same reasons that it'll make it easier for you to do adequate evaluation of your algorithms, it will allow me to do that on December 12th as well, or whenever I get to grading it. Okay, so sorry about that, but those are good fixes, and thank you for the help for bringing that to my attention. Okay, week 15. So, I forgot to tell you. I'll do it in code. The other thing you see on the agenda is that the sequence for computing the average, since we're starting at 8 bits, we have to scale up to 16 bits. So CBW in the agenda on line 14, that means convert byte to word. So what that does is that kind of safely scales up an int 8 into an int 16. And the way it does that is that it scales up. Maybe we can just do it and I'll show you that as well. But anyway, it'll take the 8 bits in AL, and if the sign bit is a 0, we'll copy all zeros into AH. If the sign bit is a 1, it will copy all 1s into AH, and that preserves the original positive or negative value. And then the IDIV instruction itself, in this case, I use the B register to hold the size of the array, the denominator part, and then AX is where we do the computation into, so that we get the average itself, the quotient in AL, and the remainder in AH. So technically it's a little bit easier than the weird DXAX stuff. So that's the other change, since when I was talking about it, I was speaking in 16 to 32 bits last week, and what it needs to be is 8 to 16 bits. Okay. Now I think I've covered all that crud. All right, so for this week, it's possibly the first thing that's going to kind of look like assembly language to everybody, because we're going to get rid of the if statements in our lab this week and replace those with the way that we do control of flow or flow of control, depending on which direction you like to say that. The way that we do decision making in assembly is not with if statements. It is using the compare instruction combined with jump instructions combined with labels is what they're called, but I think of them as targets. Or targeting labels. That's kind of my personal terminology for it. So I think this is actually going to look like what a lot of people think assembly might look like when they come into a class where assembly is used. So this is just so you can kind of gain an insight into what if statements are trying to help you with. So if you go into a language like Go or C++ or whatever, and you see an if statement, those if statements are actually there to try to make it easier for you to express your decision-making logic than what you can do at the assembly level. That said, some people actually tell me after they do this content that they think that the assembly style is actually in some ways easier for them to understand. So anyway, you may or may not be one of those people who looks at it and thinks, this seems kind of easier to understand logically what's going on. I'm not one of those people. I like the if statement. Okay, so some readings. Homework as always. The lab, I'll go ahead and bring that up just so I can refer to it when we get toward the end. So the discussion, the discussion topic is the go-to statement, which I deduct points from people in all of my high-level programming classes when they use a go-to, because it's considered very bad form to do that. But I think you have earned the right, if you take an assembly language, a computer architecture class, I think you've earned the right to reconsider whether or not go-tos are good or bad things, because you will have your own experience with writing low-level decision-making. Go-to is basically what we will call in assembly language an unconditional jump, is what a go-to is. So that's our discussion topic. And then reminders. So homework lab discussion, as always. And then project 2, which is due not this coming Sunday, but Sunday, December 11th. Okay, so let me switch views and bring up the virtual machine. Get that kind of in the middle of my screen a bit. So I kind of preloaded this so I could show this to you right when we started the class. This ran.u range, I'm going to make it -10 to 10. So I was wrong. Someone asked me, can you do negative numbers? And it turns out, when I took the time to go look up the documentation, that you can, in fact, produce negative numbers. Not now. So anyway, this is how you will do the random range. And then you can still kind of pluck off the lowest 8 bits, and those will work. Although, let's use EAX for this part. Oh, I know why that didn't work. Because I have to typecast it. So anyway, I'm just going to run this little program, but just so you've seen it, this is what you will be doing on the second project for the random initializations. Using ran.u range in the range of -10 to 10, and I'm going to just build it and run it so you can see that it does in fact do that. And then I just put a little label next to all the negative ones just to kind of make them pop. So anyway, you can see that it does, in fact. I did 100 of them just to kind of get a sense of whether or not this was true. There's a 0 in there. Oh, that's fine, because that's between -10 and 10. Okay, I guess I'm okay with that. There's a 10, there's a -10. So you can, and that's good, because then you can fully exercise with random numbers your array algorithms on project 2. Project 2, not project 4. Okay, so hopefully that helps. That's project 2 related stuff. Yeah, so Druid is asking me about this typecast right here. I think on line 12. So you can correct me if I'm wrong, but this typecast on line 12 is actually required. Okay, yeah, so the typecast here, if I don't typecast it and I just say AL, well, I'll just show you real quick what happens. So the little negative label never popped out, and that immediately sort of drew my attention to the fact that oh, it must not be able, it's not doing this as a signed comparison. It's not actually detecting anything less than 0 because I'm just feeding it the raw hex value, as Druid is pointing out in chat. So yes, it turns out that that raw hex value is never going to detect anything negative. So it will never be less than 0. So I have to force HLA to look at those bits and interpret them as signed integer data, or the comparison just will never work, interestingly enough. So yeah, there's my my negative markers that popped up. And that's kind of what drew my attention to, I must have missed something, and I did. So yeah, so there's that. I'm going to make a new one now, and we'll start talking about the new stuff. So what else do I... Oh yeah, the division sequence. So I'm just going to do one manually. So this is just some little, you know, after minor updates to project. So let's just do one so that you've seen it. So let's just do something like, I don't know. Well, let's do, we'll do 99 divided by, let's say 4, just to make life interesting. 99 divided by 4. Or how about negative 99 divided by 4? That seems more fun. So negative 99 would represent the sum, and 4 would represent the size. So that you've seen the sequence for dividing 8-bit values. So I need to load up the values. So I'm going to go ahead and move negative 99 into my numerator. I'm going to convert byte to word. So what this does is it takes AL, and it looks at that sign bit in AL, and if it's a 1, then it literally copies all 1s into AH. The effect of that is that you have in AX a whole bunch of 1s and then whatever the value is in AL. And the way Tues complement works, that actually preserves even the small negative values. You can experiment with it on a calculator if you want to, but we need to take that byte, which is AL, and do the sign extension, which is convert byte to word, CBW, so that we get 32-bit numerator to work with. And then we do a signed division. And then AX is that now extended AL into AH combo. And then we could print out the quotient equals... we're doing signed here. That's the quotient. Remainder, that's what you call the other part. Equals type int 8AH. That's the remainder. I'm going to have to... no, it doesn't matter. I'll just let it run. It goes fast. So this is the sequence. Assuming that you've got your sum somewhere, you need to get it into AL because the division instructions are hardwired to AL. Then you do the sign extension step. The reason why we can't just move 0 into AH is because if we move 0 into AH and AL was a negative number when we're doing signed division, then we lose its negativity. It becomes a positive value. So these special convert instructions ensure that the sign, the positive negative information is not lost as we kind of promote 8-bit values to be 16-bit values for division's sake. And then be careful that you do IDiv, which is the signed version of division. So what I'm expecting to get is what? Negative 27, negative 27, with a remainder of 1. Negative 1, I think. Let's try it out. Negative 24. and a remainder of 3. Well, that's just because, you know, I can't do math. These are 24, 2, 8, 19, not 29. Yeah, 19. Yes, okay. So I guess the computer's right. It's a negative 24 with a remainder of negative 3. So that's just there. So I will include these with the sample code. In fact, let me just go copy it over there. So that's the 2 kind of new things that the changes to the project requires, that you do a ran.u range from negative 10 to 10, and that you change, that, which is not part of the update, it's just part of me saying it wrong last week, that you change the division sequence to deal with 8-bit values. Okay, so that's that. Now we can actually move on. Now finally we can move on after I clean up my mistakes to some new. Okay, so now we're back from me trying to kind of clean up the project 2 stuff and give you some updated hints about that, to what's the new content this week, which is how do we actually do decision making at the assembly level. It will not be in the form of if statements or switch statements. It will be in the form of compare instructions combined with a variety of different jump instructions. So the first thing I'm going to do, though, is just put some labels in here. So 2. So these things here, label 1 colon, label 2 colon, they're called labels, although I like to think of them as jump targets. But anyway, but officially in x86 assembly, they are called labels. What they do, well, they don't do anything, but they create addressable locations in your code that you can jump to. But by themselves, they don't do anything, and I'm going to start just by proving that. So I'm going to do a standard out.put before label 1. And I'm going to do a little bit of copy and paste so this part goes faster. So now we have after label 1, before label 2, and then after label 2. So I usually start with this just to get people over this small hump that they have about these labels. So what do labels do? They don't do anything by themselves. They do nothing by themselves. And I'm going to prove that by building this program. So you'll see that the output is before label 1, after label 1, before label 2, after label 2, with no seeming interruption in the program's flow at all. And that's because labels don't do anything. But they can be used for things. So just sort of to get that worked out right at the start, labels don't do anything. And you'll notice that's the first element I have on line 20 in this part of the content to talk about labels. They don't do anything. At least not by themselves, they don't do anything. But let's do a jump. So this JMP, this is called an unconditional jump, which means that it is jumping not based on any particular condition. It's just going to jump. So I'm going to jump, and what you do is when you write a jump instruction, you give it a label as a target. So I'm going to jump to label 2. So this is an unconditional jump, which means that no matter what, there's no condition that will change this. When the program reaches this point in its execution, it will jump to label 2 and then proceed with whatever executable statements follow. So what this means for us that we're about to see is we're going to jump over the instructions on 13 and 14, which means we will not see them execute because they won't execute. We're jumping right over the top of them to label 2 and then continuing our execution from there. So the reason why I went from before label 1 to after label 2 again is because this unconditional jump used this label as a target, jumped across everything in between itself and that label, skipping it all, and then continuing execution, which is basically what if statements do. Basically, if statements are ways to jump over code. Okay, I'm going to do something naughty here just so you can see that. So you can also jump backwards. So you don't want to do this. I mean, you can if you want to, but just heads up. In fact, I might ask before I do it. So when this program executes, it's going to print before label 1. It's going to jump to label 2. It's going to execute what can be executed after that point. And when it hits label 1, it's going to jump back to label 1 and then start executing from there. So can anyone kind of see what's about to happen here? It's a bad thing. That's right. So a loop is correct. It is a loop. And in fact, it's one of those bad kinds of loops. There you go, a loop in chat. That is an infinite loop. So you need to be careful of this, just like you can in a high-level language. You can accidentally create an infinite loop. Yeah, and Linkerage and Isnom also have that. That is, it's a repetition, and Isnom also said that's a forever loop. So exactly right. So be careful of that kind of thing. You can easily, just like you can in a high-level language, create an infinite loop with badly designed jumps. Okay, so you will see, by the way, that we do use unconditional jumps. In fact, probably we're going to see them in places today, but we'll also see a lot of conditional ones. Okay, so before we move on from that, I want to talk about the labels themselves. So the labels themselves have the same naming rules in HLA as anything else. So I could have called it label 1. I could have called it label 1. Any name that I could use for a variable or a procedure name in HLA, I can also use for a label name. Now, for me personally, I like to do labels in all uppercase letters because I find it easier to see them. You get very messy looking code when you do low level decision making like this. So I like to make my labels pop on the screen. There's another thing that I do with labels besides naming them this way to make them easier to see. So like using the underscores and stuff, I just find that easy to see. The other thing that I do, because you can do this. Oops. You can place them wherever you want them to be. I, most of the time, will try to have them hanging out as far to the left as I can. Again, because they can be hard to find in a large program where you're doing low-level decision-making like this. So I like all uppercase. I like to use underscores because underscores kind of catch my eye when I'm reading code for naming the labels. And then in terms of where to place them for indentation purposes, I generally kind of hang them out pretty far to the left, if not all the way to the left edge, just so they are super easy to find. because you'll see it doesn't take a whole lot of logic to get just a nasty, nasty mess of them. One last thing about labels. You can't reuse label names because how does the system know which label? If you have two labels of the same name in your code, I'll do it. If you have two labels of the same name in your code, how does the jump instruction know which label you're targeting? So anyway, we're getting the rare kind of useful HLA error message here. It says duplicate label definition. So anyway, it won't let you do that. So you will find yourself using numbers to differentiate your labels from each other. Anyway, so there's the basics. Labels and how I like to do them. The label itself has a colon after it. The jump does not. The jump is just a regular instruction, more or less, that has a semicolon at the end. Okay, so let me move that stuff to the bottom. And then we will look at doing these things in real life. And I'm going to put some static variables in here because there are some important differences to note when you are comparing signed integers versus unsigned integers. So the comparison instruction, CMP, doesn't care if you are feeding it signed or unsigned integers. But the jump instructions actually do care if you feed them signed or unsigned integers. So we'll start with unsigned. So I'll call this a UX uns8. I'll go ahead and give it a value, just something like 10. A UY uns8. I'll make it be 9. And then a UZ uns8 equals, I don't know. Maybe I don't need the UZ just now. Okay, so unsigned. So I'm going to use a fancy word here, but it really is not that fancy a word. So we're going to do some examples with unsigned comparisons. And the thing to note about unsigned comparisons is that the jumps will use, the way I like to describe it, is that the jumps will use above and below semantics. And what I mean by that is that the jump instructions themselves, greater than, for example, will be jump above. That's the above part of the semantics. Less than will be jump below. That's the below part of the semantics. We have jump equal to, which doesn't really care if they're equivalent. There's no special semantics for that. We have greater than or equal to, which is jump above or equal to. So do you see kind of the above, above, above for unsigned integers? Less than or equal to, which is jump below or equal to. And then finally, not equal to, which is jump not equal to, which doesn't have a special semantics to it. So by semantics, I just mean that the instructions use the lingo of above and below. Jump if above, jump if below, jump if above or equal to, jump if below or equal to. Fortunately, equal to and not equal to don't have special theme or semantics to them. So jump if equal is JE, jump if not equal is JNE. And then I'm gonna probably, well, I'll at least write a few just kind of normal high level ones. And then we'll translate those into low level instructions. So let's just do a simple kind of if. Can't do memory to memory comparisons, which is a bummer. So we'll move UX to AL, and then we will say if AL, well, let's say if UY is less than AL, then y less than ux. High level style, right? So I put the u on the variable name just so that we're kind of constantly reminded we're talking about unsigned integers. And unfortunately for doing this kind of stuff, if it's signed or unsigned, that matters. So we're doing unsigned integers here, and the instructions are all going to be themed, or their semantics are going to be above, below kind of terminology. All right, so let's make sure that works. Just at the high level. It'd be silly to translate bad logic into low level. So now let's translate this into high level stuff. So the basic idea here is to recognize that this if statement, should it fail, it actually jumps across without executing the code inside the if. So there's a jump going on here. So the way you do this in assembly style is I will compare. I wonder if we can compare uy with ux directly. Before I do anything else, let's just see if that compiles. Okay, it does not, which is what I thought, but you never know. So we'd have to do this same kind of setup. So we're going to compare ui with the ux value, which is in AL. So this is how you set up to do low-level decision making. You will fire off a comparison instruction of the two things being compared. If you have, by the way, complex logic like something and something or something or something, that's just a big pain in the rear to do at the low level. So just heads up about that. We won't need it for our project, but maybe we'll do one just so we can see what it feels like. Okay, so you fire off a compare, and what the compare does is it actually subtracts one of the values from the other, and then it sets some of the E flags bits based on the result. You don't have to worry about that at all. All you have to do is use the desired jump instruction immediately after the compare. That is the important thing to you. So I'm comparing these two values, and for me, I often find that I write the low-level logic kind of upside down from the way I wrote the high-level logic, because for me, the way I want to write this is to think about that jumping across kind of thing. And when you do the if statement, you're actually going in as opposed to skipping over. So anyway, I often think, well, if the if statement's going to let me in, then the low level, the assembly style logic is going to get me over. So what would get me over is, oh, I forgot, by the way. Well, that's fine. So if the result of that comparison is that ui is either above or equal to, then I need to get to an end if. Now I haven't created that label yet, but this is often how I find it works out best for me, is to look at the high level one and then write my low level logic in reverse. I'll write it in the same order just so you can see the difference. So what is this saying? This is saying if the result of this comparison was that ui is above or equal to AL, then I'm going to jump to an end if label, which I like to jam up with the colon there against the left, as far left as makes sense. And then I just have to sort of imagine, what do I do if I don't kind of jump over? Well, if I don't jump over, then I'm actually doing the original statement. And I usually do kind of some lining up. So if you like the way it looks, kind of with the label set up like an if statement, that's fine. There's no rules prohibiting that. I just know that I lose my labels pretty easily when I'm doing this, so I like them way out where I can see them easy. Okay, so can't do memory to memory comparison, so I move the value of ux into AL, and then I fire off the comparison instruction. where I compare the unsigned value uy with the unsigned value in AL. And then I jump if the result of that comparison was that uy is above or equal to the value in AL, then I'm just going to jump to this label and nothing happens. If the result is anything other than uy was above or equal to, which would be less than, then I print the statement. So that's what we expected. I'm going to write it sort of in the normal way as well, but I often find that I get to my low-level decision making more efficiently if I kind of deal with the reverse of the logic, because the reality is what the if statement really does is jump over, not jump in, at least in the way my mind conceives of it. The if statement kind of allows you to get in, but really what the if statement does is when it fails, it jumps over. So for me, that's how I would end up writing that statement. But let's do it. I'll put one in between. I'll do the same statement kind of with the same structure as a normal if statement. So can't do memory to memory, so I got to copy UX into AL. And I know I don't need to repeat that, but just so that each section is complete. And now I do the comparison. So I'm going to compare UY and AL. And then there's really only to mirror the same logic, I have to say, well, if the result is that UY is below the value in AL, jump below. If I'll call it the if part. So you can kind of see where the numbers might. So jump below if one. All right, so I'll put an if one here with a colon because that's how you set up the label part. So if I don't, so the if one is actually this. Hopefully that makes sense. So if UI is below AL from that comparison, then I'm going to jump down here to what would have been the if part. But if I don't do the jump, then I have to deal with the fact that I didn't jump. And if I didn't jump, then I got to get out. Label, and then I'll make this an end if 2 to differentiate them. Okay, so here is kind of the ordering of the traditional if statement, where I run the comparison and then I trigger my behavior on the result that UI was below the value in AL. So remember, above, below, these are unsigned integers. So if UI is below AL, I will jump to if one, and then I will print out this statement. If the result wasn't jump below, then the very next thing I got to do is get the heck out of here by jumping over, which is how the if statement would do it, jump over that statement that I would have executed. So there is the high-level version of it. There is the version of it that kind of is an exact match of if UI less than, which is kind of messy if you think about it. There's 2 labels and 2 jumps required to do that. And then there's the way that I usually end up finding myself doing it, which is I kind of set my mind to think of the logic in reverse. And when I do that, I usually get away with less code for the effort of thinking of, well, what would I do in reverse? Anyway, so there is 2 different versions of that same if statement. I'll compile it and make sure that it runs. Okay, kind of crazy stuff. And you can already see, by the way, that's just 3 if statements. And because I'm doing it in the low-level style, it looks terrible. Meaning there's a big mess already on the screen just for 3 little if statements. Okay, so there's some if statements. Let's move those down and do some. And I'll put a little separator in here. as I move these things down. Okay, so now let's do an if else and then an if else if else, and that's most of what you need to see. So let's see if we'll do an if else. So we will do if let's do it in reverse. So let's yeah. So we will say move uy this time to al. So if ux is less than al, let's remind ourselves that unsigned uses the semantics of above, below. What? Okay, so there is the standard if else, which in this case should be ux is above or equal. So that's what's expected. So now let's translate that into assembly code. And I'm just going to go with whatever kind of feels right to me, and then we'll see if there are other options. So let's do it low level style. So to do a setup, we'd still need to do this part because you can't do memory to memory comparisons. And then we would fire off a compare. So we will compare ux this time against al, because we want to know what's the relationship of ux to this value. And then it's very important that you do the jump immediately. You can't insert another instruction right here, or you break the flags register settings potentially. So a comparison has to be followed immediately by one or more jumps related to that result. Okay, so what do we have here? We have, we want to know, is it less than? So this one might look okay if we do it this way. So if ux was below the value in al, then we will go to if 1. So I commented out those other labels, so this is safe. So I'll go ahead and set up the if 1 for when I need that. So if ux was below, then I would end up doing this thing. In fact, I'm going to do this the long way. And then I could also say right here, but maybe it was above or equal to instead, and then I can have an else part. Where I do this. And then something that you can't see, but that is a pain. In fact, I'm going to change this value so that it will be below. So let's make this be 100. So now ux is below, and I want you to see what happens on this second sequence. Okay, so there's a problem on the second sequence. The first sequence seems intact. In fact, I'll comment it out just to be sure it's not the first sequence being stupid. Okay, so in the second sequence, something is wrong because it's printing both of these statements. So this is kind of a, has anyone caught on kind of quickly and can detect the problem here? Why is it printing both below output and above output? Which may be hard to answer in chat, but I'll give you a shot at it. Yeah, it's tricky. So the thing to remember is that the labels don't do anything. So if that's right. So isnam is correct. So it's not really calling, but you're correct, isnam, that both of these things are being allowed to execute. So how does that happen? Well, we know that I changed the value of ux to be 10, which is below the value in UI, which is 100. So I'm going to jump to this label and execute this. And barring anything else, remember the labels don't do anything. So if I jump to if1, I'm just going to execute. I'm going to go right through this label because it doesn't do anything and execute this as well. So yes, so Alu is right as well. It is jumping to if1 and then it just starts going because the labels don't do anything by themselves. So something has got to happen after line 29 so that it doesn't just flow through to line 31. So what has to happen here after line 29 to not accidentally allow this next part to happen? We will end up doing that eventually. So Druid says maybe we can kind of reverse the labels somehow and get the behavior we want, which is true. We probably can. The trick is, though, in a situation like this, where you got kind of a decision tree, once you've hit and executed that part of the decision tree that you want, you got to get the heck out of here. So yeah, Islam, it's kind of like a break. You're right. So yeah, we have to use an unconditional jump. So if we get into the if1 part, then we have to use an unconditional jump to get over the else part so that it won't execute. So this is kind of the whole decision tree, translated kind of directly mirroring the high level version. So you're going to find yourself doing this a lot. When you get to that part of your decision tree, and now you got to get out. You got to jump somewhere to get past all the other junk that happens in the meantime. So if I get to this part, I'm going to print below, and then I got to get the heck out with a jump. I don't need to do that after line 32 because it naturally just flows to the next line of code anyway. So yeah, you got to get the heck out with an unconditional jump here for this to work. So I restored the original one. I'm going to leave it commented out for now. So there it is, just that one. So the unconditional jump fixes the problem of accidentally kind of flowing through. If you've had a C++ class, by the way, the switch statements have this same problem, or you could consider it a feature depending on your opinion. But in a switch statement in C++, if you don't put a break after a case, it flows through to the next section. Which is this same kind of situation. All right, so there it is translated. Is there another way to do this? Well, let's try. Let's see if there is another way to do it, kind of in my preferred style, which is, can I reverse the logic? I don't think I'm going to save myself much space, but here's one thing that I might do is to reverse the logic and say, well, I'm most interested in UX being below. So I'm going to deal with the above or equal to. So jump above or equal to, else 2. In which case I'll do this above or equal part. And then the thing you can do, and it takes some practice, but you think, well, if I don't do the jump, what does that mean? If I don't do the jump, what that means is that the comparison was actually a below result, not above or equal result. And I can simply just allow the program to flow right into the below action. So if I don't do the jump above or equal to, it's going to naturally flow into the below action, which is what I want. I still have the problem here that if I just leave it at that, it's going to flow right through into the else part. So I still actually do have to get the heck out of here. But I was able to save myself one label, and that, based on your opinion, may or may not be a good thing. But it's a little bit simpler of a sequence with less labels and less jumps. There's one less jump and one less label, so you could argue it's a little bit simpler to do it this way. Should say below twice in the current version, which is correct. So yeah, there you go. Now if I reverse this, by the way, so if I put the y back, then I should see above or equal to in both cases. Which is correct. So getting a little bit hairier as we get to the if else statement. And let's go ahead and make life more miserable. So let me put a marker in here between the sections. And then go pull this stuff out, and let's do a bigger decision tree. It messed up my formatting, but I'll live with it. Okay, so let's do one last one, and then that's most of what we need, and I'll just quickly show you the signed form of this stuff. So still comparing these two unsigned integers. So let's do something like this. So we'll say if, let's make it 101. 101. So if ux less than 10, then small number else if ux less than 50, let's say, number if ux less than 100, then large number else. Anything else is going to be 100 or greater. I could if I want to. No, I'm not going to worry about it. We'll just play around with the values. So this should give me a very large number, and then I'm just going to test. So, well, let's test them all. So we'll start at 1. I'll run it and just make sure that we get a small number off of it. Small number, and then we'll just say 49, which should trigger a medium number. And we'll say 99, which should trigger a large number. And then we'll do 101, which should trigger a very large number. So we know the basic logic works. Okay, so there's my tree, and now I'm going to translate that into assembly language. This one's going to be nasty because there are 3 comparisons, so that's kind of a bummer. So anyway, I'm just going to do it, and I'll try to comment on it as I'm doing it, but the initial comparison is ux with 10, and I believe that I can get away with a comparison against a literal value like 10 without being hassled. I can. Okay, so how are we going to do this? Bunch of different ways to do it. So what I'm going to do is I'm going to say, I forgot things like, by the way, there's also jump not above, jump not below options as well. but I'm going to say if it's a jump not below 2, else 1. And then just kind of work it out in reverse. So if I don't jump to the else part, that means that it was below 10, which means it was not below. So I will do this thing, and then I need to get the heck out of here. So my first label is actually my last label, which is getting the heck out of here. Now I will do the else part. So in the else part, unfortunately, I have to fire off another comparison because I got to compare it with 50 this time. And then I'm going to do the same thing, kind of jump not below else 2. Oh, so Druid asking a good question, like why use not below or why not, use above, or it's just sort of the whatever your preferred kind of language of the jump instructions sounds like to you. So yeah, so jump not below is the same thing as above. And the only reason why not below is there is just, I think, probably because some programmers would prefer to kind of think in terms of it wasn't below as opposed to it was above, which are the same thing logically. So yeah, I think that's just a matter of personal preference. So yeah, I was kind of, for me, I was reading it as, what do I want to do if UX wasn't below? Or in other words, if it's not below. Okay, so if I don't leave here, then I'm doing the medium number part. You can see, by the way, it's already kind of starting to get tough to track. And then we would do the jump, get the heck out of here part. Okay, and then we need the else 2. And you can number these, you can label these in different ways. Like you could say like else check 50 as a label. If you wanted, if that kind of makes more sense. So yeah, that's a good question, Druid. Will a value less than 10 trigger all the conditions? No, because of this jump right here. So if I don't have this get the heck out of here jump, then yes, a value less than 10 would potentially trigger all the conditions. But because I have this jump right here, then none of the rest of them is ever going to get checked. All right, anyway, I'm going to leave it with my else 1 and else 2 stuff. Jump else 2. Got to run the comparison again, this time against 100. Jump not below else 3. Which would mean a very large number. Otherwise, I will do a large number. And then get the heck out of here. Okay, so there's that tree, maybe, translated into... by the way, I've noticed some people do this little trick in this class. They will just put a label at the top of the tree. Even though it doesn't do anything, it helps them kind of keep track that this is a complete tree. And I can even say this. I could say else if 1, else if 2, else 3, that kind of thing, if that helps. So you can totally like add an extra label here and there if that helps you kind of keep the tree together in your head. It's not needed, but it also doesn't do anything. So this if 1 does no harm to anybody. Unless it's a duplicate. But it does maybe for some people make it more obvious that this is one big tree. So I'm at 101. So I'll just go backwards. I should get two very larges here. Okay, two very larges. Go backwards. So this should just be large. 49 was next, which should be medium. And then finally, I'll just put 9, which should be small. Okay, so you can kind of see how quickly this thing can get really, really hairy to deal with. Some people like it. I'm not one of those people. I think it's pretty difficult to not make mistakes. If you leave off one of these get the heck out of here jumps, then you're going to get more behaviors than you wanted. So Druid made a good point. So let's just do it. If we forget one of these get the heck out of here's, what would happen? So if I just leave this one and I end up with a small number, what happens is I'm going to flow right into this next section and I'm going to rerun the comparison and it's going to succeed. And I'm going to get both a small and a medium number for outputs. So those get the heck out of here jumps are very, very important to avoid undesired outcomes. Okay, so that was all unsigned integers stuff, and what I should have done is called this like, yeah, let me do these separate, 15a and 15b. So now I can open up week 15 again. All right, so last thing, and I think we can call it a day. So the last thing is, this is the other version of that program. So yeah, I'm safe to wipe it out. I'm going to call it 15B so that I get them uploaded that way. All right, so let me clean this one out and just show you quickly the signed comparisons. So if these were signed integers, then almost everything stays the same except for the jump instructions. So for signed comparisons, but the jumps use less than, greater than semantics. So they look like this. If you have less than, it's jump less than, not jump below for signed integers. These are just some of the things that make pure assembly language a pain in the ass to work with. Sorry, I said a bad word. Pardon me. They make it unpleasant to work with. So jump less, jump greater, jump equal, thankfully, is the same. Less than or equal is less than or equal. So the less, greater semantics, greater than, equal to is jump greater than, equal to. Not equal, thankfully, is jump not equal. So that part doesn't change. So notice though, we don't use the JA for above. We use JL for less, or JG for greater than. And then we also have the kind of extras, if you like the language of them, jump not less, jump not greater, for signed comparisons. So I'm just going to do a quick one, which will be like we'll just do is IX greater than IY. So we've got to get IY into AL, and then we will do a comparison of IX with AL. And then, you know, the various ways that you can do that, but basically we can say jump not greater, which is the same thing as jump less than or equal to, right? So if it's not greater, then it would be less than or equal to. Either way works. Um, so that's just a personal preference. If you like to think, well, it wasn't greater than, that's when I jump. Or, well, I can make perfect sense of the fact that not greater than means the same thing as less than or equal to. So less than or equal to, we'll call that the else part. We can also call it, by the way, the, well, you can call it whatever you want. You can call it the false part, whatever you like. And then the jump to get the heck out of here so that the one section doesn't flow into the next. So that's very important. Otherwise, they just kind of flow together. So in theory, Ix is greater than. So what should, in fact, happen is that we should see is greater than, and not the other way around. But we'll test both. Oh, wrong program. B. All right, so -1 is greater than -100. That's true. If we switch them, then now it's less than. We're just checking our logic here. So -101 is not greater than -100, meaning it is less than or equal to. -100. So that was just to kind of show you in context what the signed jumps look like. So the comparison stays the same. It's the jumps that change. And then the main thing to remember is that the comparison, the jump has to immediately follow the comparison. You can do a sequence of jumps if you want to. So you could say, for example, well, I'll just do a different one so you can see that. We could do something like this as well. So let's just say, what is Ix as it relates to Iy? So we'll move Iy into Al to get the good setup. We will compare Ix with them. And then we will do jump above, not above, greater than. I also sometimes will just kind of hang out an extra underscore, and that's again because I like to see the underscores because it helps me find my labels. Jump greater than. We can do so we can do a sequence of jumps to different sections of our logic tree as long as those jumps immediately follow the comparison. So we can do this: jump greater than, less than, equal to. And then we can have the whole tree kind of down here. And I'll just steal this. Greater. Less. Nope. Equal. Why does it always jump to the left? I don't know. So that's kind of a which is it? Greater than, less than, or equal to. Does anyone see what I am missing here? And that'll be kind of where we end the day, I think. So what's missing here? That's right. So Druid is exactly right in chat. What these are missing is the jump to get the heck out of here um, after each part. So, yep, if we don't jump when we get the greater result to the very end, then the less result's gonna fire off accidentally, and then need to jump from there. We don't have to do a jump end after the last one. You can put a jump end here, but all that does is allow the program to basically go where it would have gone anyway. So the last one you can, but you don't need to put that get the heck out of here jump because the program was going to go there anyway. So let's try it. I'll do a greater than first, just to make sure the results are good. All right, so one is greater than 100. Then we will do less than. And then we will do equal to. Just to show that that second section works. So you can string together multiple jumps from that comparison, but the jumps have to happen immediately after the comparison. Don't do anything after the comparison but a jump. The moment that you do anything else after a comparison that's not a jump, you break the flags and the jumps have no meaning anymore. So jump immediately follows a comparison, but it can be multiple jumps based on multiple outcomes of that same single comparison. So some people like this style a lot because it just kind of makes sense to them. To me, it seems pretty clean. Okay, so all of those things are going to get loaded into the lecture page for today. So there'll be the week 15A and 15B code. There'll be the little samples to help with project 2. All those things will be there. So I think that's everything. I didn't look at the lab. I guess I can switch over real quick just to call your attention to what the lab does. All right, so here's the lab. Basically, your problem is, and they're probably numbered. Yep, so here's number 1. And this one was kind of made to be challenging. So you have to find the high-level things and translate them into low-level things. And the trick is to be careful that you don't duplicate labels, of course, because you're not allowed. So if it were me doing this lab, I would notice that we have this outer if statement that starts here with this if, and then has an else if, and then has an else if, and then has an else. I would probably actually start from the outer if and then work my way to the inner ones. So there's a second one, there's a third little tree, here's a fourth, which is just an if, so that one's one of the easier ones. Here's a fifth that also has a little nested sixth in it. So the goal this week is to translate as many of those high-level ones into low-level ones and retain the original behavior of the program. So the first thing you ought to do is compile and run the program. It's a complete program. Make sure that you understand its functionality, and then see if you can translate the high-level stuff into low-level stuff while retaining the same functionality of the program. So how many are there? There are 7 translations, which I've done more than that sitting here. Some of them are easier than others, like this number 6 looks pretty easy. So I would probably work from the outside in, but you might choose instead to work from the inside out. Just kind of have to just get a feel for it by trying it. You may never do this again in your life, so this might be kind of your one chance to get a feel for what actually happens underneath an if statement in a high-level language is this mess that we're doing right now, which I find interesting. It's an interesting puzzle to solve. Okay, yeah, so there's 7 high-level decision trees in there. Next week, we do the loops instead. So we do the loops low level. And the loops are arguably a little bit actually easier than the decisions are. Okay, so that's all I've got. I've got 3 samples to upload to the lecture page, and beyond that, please help me get the word out about the small range updates on the project. That will make your testing life go a lot better. You'll get a lot more consistent results and be able to actually um, expose bugs if there are any. Okay, I'm going to finish with that. So I will see you on Tuesday afternoon next week. Canvas Inbox, Piazza, office hours. As always, if you have questions this week. Otherwise, hope you have a great week, and I'll see you next Tuesday.